That's the access point itself. What I'm going to do next is turn it over to Peter Lane to talk a little bit about the performance that you can get from this device and maybe do some live demos.
Definitely. So you've heard a lot of the numbers that are out there, right? With 11N, you were looking at 450 megs for a 3-stream device, 150 for connected data rate for a single-stream smartphone. Real-world TCP throughputs were obviously significantly lower. You're looking about 95 megs and 280 for a 3-stream device. With 11AC, we'll show you some demos here today where we're seeing up to 830 megs of TCP throughput on a 3-stream device and 240 on a single-stream smartphone. That's a lot of throughput for a smartphone, and a lot of you are probably wondering, why do you actually need that much throughput on a smartphone? But remember, we're also dealing with congestion. We're dealing with all the smartphones that are out there trying to get on the network at the same time. The faster I can talk to one person and knock it off the network, the more airtime is available for everybody else that's out there. So we're seeing a big boost in performance. We're actually starting to see the smartphone devices show up. I'm sure you're all aware that the HTC One and the S4 are available. I think we're actually using an S4 in the testing here. So we'll run through some of that in just a second. So let's hop over to the demo. You could hit the button. So the first thing that we'll take a look at is the performance. So this is a 3-stream TCP downstream throughput test using Ixia Chariot. The standard high throughput script that they've built in. There are no changes to the scripts that we're running through. And up here at the top, you can see we're getting an average of 777 megabits per second, a minimum of 772, and a max of 783. So we're coming right around 780 megabits. That's in this room with all of you here. We'll actually run the UDP downstream test live so you can see it. And all this is running off of this AP right up here in the ceiling. I don't know if you noticed in the front. That's our new AP 225 that's running. And I've got the laptop and the smartphone are over here in the corner if you want to take a look at them a few minutes later. So now we're going to run the UDP test. Bear with me. It takes about 30 seconds to run. So again, there have been no changes to the script here. It's the standard Ixia Chariot high throughput test. Got about 20 seconds. So we're seeing very, very good performance, good connected data rates. I see some of the bloggers seem to be running sniffers through the air, watching what's going on. Hopefully it looks pretty good. So again, one of the things to keep in mind with 11AC is it's not just about that end user. We hear a lot of times, I pulled a gig to my desktop a few years ago. No one uses anywhere close to that. 100 meg is fine for all of my users. Why do you need to worry about migrating from 11N to 11AC? And it really is about the number of devices that are on your network. When you have 50 or 60 users sharing that same 11AC radio, every second counts. So the faster you can get them off the network, the more you can have everyone else running. So here the UDP test just finished. So downstream, looks like we got about 910 megabits per second of throughput. You can see there's a little fluctuation going on there, but it's pretty good given the fact we have about 50 people in here, and I see pretty much everyone has at least a laptop open, and most of you smartphones and tablets as well. So there's a lot of stuff going on in the air. It's not a perfectly clean lab environment. In lab tests, we do see a little bit higher, but I think 910 is pretty impressive. Let's take a look at the smartphone test results. So now we're going to run the same test, or pretty much the same test, downstream throughput to the S4 we have sitting in the corner. So that's a single stream 11AC product. So these are obviously 80 megahertz channels that we're using right now. And this is a standard 1 meg throughput test. I think we changed the file size from up to a meg from 100K. That's the only change that was made to the script for anyone who wants to try and reproduce these in their lab when they get a hold of a unit. So we're running through now on the Samsung. And we'll see, was this the TCP or the UDP?
This is TCP down.
Okay. So TCP down, looks like we got about 221 down to a smartphone. So the max connected data rate for a single stream smartphone is 433 megabits. We can expect to see probably 220 in the real world. So this is about 15 feet away, but it is fairly line of sight. It'll obviously get worse if you're going through walls and things like that. But all in all, we're seeing a big performance boost. There's one more test we're going to run. We'll run the UDP data. In a minute, Kirti's going to talk a little bit about Client Match, which is really designed to help solve some of the signal issues that we're running into to help make sure we can get the best 11AC rates as we go through this. We're excited to start to see the 11AC clients come on the market. We still haven't seen a purpose-built 11AC chip in a laptop yet. We're using a test client here on the laptop. The smartphones have shown up first, which isn't too surprising given their very short product life cycles. They get turned over very quickly. We're expecting laptops to start showing up the next couple of months, and a very high number by kind of the buying season, this holiday season. So here's the TCP throughput. We actually did a little bit better. We got about, sorry, this is the UDP?
This is the UDP.
Yes, so this is the UDP test, about 260 megs of throughput, 258 average coming through. So that's some of the 11AC throughput numbers, real-world testing, so you can take a look. And I will pass it back to you, Kirti. Can you hit the button?
Thanks, Peter. So that's just raw performance, right? And what we were seeing there is an AP mounted right there in the ceiling, the client sitting right here. And that's really what it takes, to be honest with you, with 11AC. The distance from the AP to the client needs to be fairly low to be able to get the high data rates of 11AC. And as we all know, if you look at Wi-Fi, performance is more than just being able to show that benchmark test, right? If you look at the real environment, your performance obviously depends a lot on the location that you are relative to the access point. Depends on who else is on the air with you, who you're sharing the air with. Depends on mobility, which changes the dynamic load on the network. People come in and go out, and that changes what's going on in real time. And then, of course, every app, mobile app on the network behaves differently. An iCloud type application is a pure background application. It's just uploading, syncing to the cloud in the background all the time, not time sensitive, whereas Microsoft Link, for example, very, very latency and time sensitive from an app perspective. So the question then becomes, in the face of this such diversity of devices, applications, user mobility, how do you really deliver the performance promise on 11AC? And to really get a view of this, the most fundamental performance graph of Wi-Fi that everyone compares to is rate versus range. And you go back to this, and it's a typical graph of performance where the further away you go, you move from the access point, the lower your performance gets. And to the point where an AC client talking to an AC access point at a sufficient enough distance away from the access point, you're down to 11G rates or even lower. So what the industry has focused on until now has been techniques like beamforming, and we have beamforming capabilities in this access point as well, which really are about pulling up that performance at the far end of the curve by increasing the signal-to-noise ratio and getting a little bit more gain. And what we think needs to happen actually is not focus there. I mean, that's good stuff in places where coverage is all that you need and so on, but in high-density areas, you need your clients to be operating in a range where beamforming is not the requirement. It's where you're much closer to that particular access point. That's really how you're able to deliver on the capacity and promises of AC. Now, let's take a look at what happens in the real world, right? You go out there, this is a classic floor, you go deploy a few access points. The first generation deployments tend to be coverage oriented. So all you do is deploy a small number of access points, and you're covering the entire floor using those access points. The quick recipe from everyone is add more access points. And by adding more access points, the hope is that you've increased the capacity in your network, not only providing coverage, but more capacity. But this belies how clients actually behave on the network. From a client perspective, what happens is once an iPad, let's say, comes into this network and connects, the first time it finds an access point, it associates to it with a very good signal strength and potentially gets a very high performance at that particular location. But as we all know, these are mobile devices, they roam around. And as they roam throughout the facility, the signal strengths get weaker and weaker, and the devices are programmed to be much more connected to home networks, so they try to hold on to that access point for as long as they can, even though the signal strength starts to get weaker and weaker. And beamforming only makes the problem worse, right? What I'm doing is pulling up the performance at the edges here, but there's an access point right next to it that I could be connected to and providing a lot better performance versus trying to optimize my link to a device that's far away from me. Now, this is just one device, and as we all know, networks have many devices, so if you have a lot of poor links out there, what's happening is you may have AC in your access points, AC on your clients, but you don't get the performance, promises of AC. So this is the reason why we invented a capability called client match. The client match is basically taking a view of the client's perspective of what it sees on the network and making decisions on behalf of the client to move the client to the best access point at that particular point in time. Okay? So there's two pieces to this. The most important piece is actually the measurement and collecting the client's perspective. What is the client seeing when it is far away from the access point? Which other access points is it seeing? At what signal strength is it seeing those access points at? And once you have that composite view throughout your network of various clients seeing various access points at different signal strengths, you make a decision on the best way to balance load throughout your network. And that's really what client match is. And the way it works is, going back to that same example of a floor plan with poorly optimized links, once you invoke client match, what ends up happening is the devices are all moved to access points that are far better choices for this particular client, for a given client to connect to, increasing the signal strength for those particular devices. And this is simply link optimization. What I'm doing is, if you have, let's say, if you're used to 5 bars, and you walk away and your bars become lower and lower, you may be at 2 bars, you get back to 5 bars. And that's a good first step to optimization. But as load continues to increase and you've done link optimization throughout your network, you end up, let's say, adding more devices, simply just invoking the layer 1 link optimization algorithm for client match, which is very cool in and of itself. But in this situation, as you can see, there are potentially access points that are lower loaded or lightly loaded than access points that are more heavily loaded. Because link optimization alone doesn't take a view of the traffic picture on your network. Right? So here, especially for high density situations, you get completely associated to the access points that are nearest to you. And in this situation, you can see a few access points in the middle with no load. And what you could do is, if you had a view of the traffic in your network, not just the view of the best link at a given client, you can actually say that there are some access points that are less loaded than other access points. And a traffic-oriented perspective of client match would be not just signal strength based, but based on signal strength and load. And this is also another capability we'll be introducing in the controller, to be able to balance load throughout your network based on traffic. Now, at this point, what I'd like to do is take you through a demo to show you what we are doing there. Because the first thing that I told the engineers when they came up with this technology was, that's great stuff, but if the administrators don't know what's going on in the back, how many times you actually steered, they'd be completely uncomfortable. I would be uncomfortable running a network where I'm doing client match in the back without a view as to how many times have I steered clients and what's actually happening. So we started with the innovation not only by providing the technology facing the client, but the logging infrastructure and the monitoring infrastructure to give you a deep view into exactly what's happening behind the scenes. Peter?
So what we're taking a look at here is Airwave, which is the network management system we use here at Aruba. And one of the first things we did is we were kind of looking at the clients and the client behavior. So we realized we needed a good metric for determining what's a healthy client and what's not a healthy client. It's actually a pretty difficult problem in terms of data rates, retries, a number of other things. So we built out what we're calling the client health metric, which you can see here. I can see the visibility across my network of how many clients are healthy versus unhealthy. And this is really comparing the actual throughput that they're getting to the potential for that client. So if I have an 11G client that can only push 54 megabits per second, if they're getting 27 megs per second, they are a 50% healthy client. And that could be because they're transmitting at a low data rate, or they're retrying 50% of the time, or something else is hitting in the network that's keeping them from actually performing like they should. So Kirti talked a lot about client match, and let's take a quick look at that. So I'm going to jump to a different screen within Airwave. This is the steering report within Airwave, so I can see all the steering events that have happened. So I can see how many of my clients are getting steered, which APs they're getting steered from, which buildings have the most steering events, which APs. So here on the left I can see by AP, which APs are steering the most, which helps me know, is this a lobby AP that people are having a hard time moving off of naturally? Is it an area that's getting congested and overwhelmed? All that sort of stuff. As I keep scrolling down, I can do it by clients. I can also look at by device type. so I can see which device types we're steering the most. We use a lot of Windows 7 here locally, which makes it not too surprising that it's getting steered. But this can also help me find clients that have poor drivers or just behave poorly on the network in general, because we'll be steering those sticky clients. So clients that don't roam well, like an Android device, well, older versions of Android, 2.3 is notoriously awful about roaming. It just doesn't. So here I can see a lot of our Android devices. We've got 631 steers for them. And I know we don't actually have a lot of Android devices on our network. Most of our users actually prefer the iPhone. So we see a fair number of those popping up here. So we're able to actually improve that. And remember, not only are we improving those individual clients, we're improving the experience for everyone around them. Because that sticky client, when it's transmitting slowly, everyone else has to wait for him to finish talking before they can talk. With this, we optimize that one client so he has a better experience, and all the other users around it benefit as well because they're not waiting. There isn't the drag on the RF space that you would normally see through a sticky client. Now, if I wanted to debug a specific client, I can search for a user. I'll just pick a username for Airwave defined for me. And when I search for him, I can now click on him. That's going to take me directly to the client diagnostics page. It's a little bit hard to see on this screen because it's so small. But along the top, Airwave is looking at each hop in the network and telling me what's healthy. So I can see the client, the network, the AP, the switch, the controller, the switch the controller is plugged into. Right now, everything looks good across the way. I can see there are a couple possible issues. But the important thing that I really wanted to show over here on the right, well, the possible issue is a low average SNR of 21. But down here on the right, I can see all the steering events. So I can see the AP they were steered from, the AP they were steered to, and exactly when that happened, and why. So I can see we have a couple of sticky client steering events that happened from AL39 to AL25 to make that client a little bit healthier. I can also hop over to the client detail page. So this is going to give me the full details of that existing client session and all the historic information. I'm going to skip over most of it. I mean, it's a wealth of great stuff, including signal, usage over time, all adjustable, their current location. What I really wanted to get to was this part down here. So here I can see all of the steering events. So again, these are my historic steering events coming in. But I can also see all the radios that are currently hearing that client. So that table of radios that can hear this client is really what the controller is using to optimize the connection. We look at that client. We see all the other radios that are out there. We see how well they hear that client. We look at how loaded they are from a client perspective and a throughput perspective and decide where that client should be connected. So if we decide that client's in an unhealthy spot, we see the healthy place that they're going to, and we can move them. And this is not just at the time of association, it's after association and later. We can leverage 11K and 11V to steer them to where they should be. So even if you've been on for 2 or 3 hours, you can end up on an AP that's healthy because of changing network environment. So that's a big departure from what we've done historically and what a lot of people have done historically to try and optimize the network. We can adjust over time while people are associated to a better place. So it's not even just go somewhere else, I'm too busy. It's you should be talking exactly to that AP over there because it has space for you, you'll have a good connection, and we know we're steering them into a good environment.
Have you been doing any testing in regards to that? Because vendors have always been trying to do this band steering and doing the whole we're too busy, go elsewhere, but the client still doesn't care. The client's still not going to listen to it. So have you seen some performance issues with trying to force a client to go somewhere where the client doesn't want to go?
We've done a lot of testing. We've been testing this for about 6 months. We've been testing it live in customer environments. We're actually running it here in this building right now. The network all of you are on is running client match. What we found is there are a couple client devices that don't behave well. Client match actually has device type information built into it. So just how the controller can say this is an iOS device versus Mac OS versus Win 7, that information gets fed into Client Match and helps Client Match make decisions. Additionally, if we try and steer you a certain number of times and those fail because the client device isn't ending up on the exact radio we want it to, we will say that client is unsupported. We'll stop trying to steer them in the future. So we actually kind of stop steering them for, I think it's about 2 weeks or a month at a time. It's not forever because they could get a new version of firmware that solves the problem and they start behaving properly. But we hold back so that we're making sure we don't cause any problems. We've been very careful to make sure that we don't cause issues with this, that we're solving them. Because that's another thing that I meant to stress a little bit more is we're really optimizing that bottom 20% of the network and making them healthy. We're not going out for that client that's 80% healthy and trying to make it 90% healthy. That little bit isn't where we see the big problem. We see the problem in the poorly performing devices out there that are making everyone else suffer. And with that, I think that's the majority of Client Match. And I will actually, there's one other thing I want to show real quickly. So we talked about the client health report, and there's one thing we do. VisualRF is the visualization tool within Airwave. And we've tied in the health visibility into visual RF. So I can now actually look at a floor plan. I'll bring up this building. And I can take a look at that client's health throughout the floor plan. And I can see who's healthy and who's not. So right now I've got a few different things displayed. Let me turn off some of this. Let's get rid of labels and hop back to the overlays. So here I'm actually looking at the health data. So on the overlay I've selected health. And when I scroll down, I can see which clients are healthy and which aren't. So anything that's green is good, red is bad, obviously, orange is kind of in between. So red means you're about 25% of the capabilities that client actually supports. So if I was a 450 meg 3-stream 11N, I'd have to be pushing less than 25% of that. I do the math, like less than 110 megs per second to be considered red and show up on here. But the idea is now I can find hotspots, right? If I routinely have a lot of red devices in the corner here, maybe the coverage isn't good, maybe there's something going on with the walls that is causing problems. I can go investigate it and take a look and really optimize the overall performance of my network. So that's the highlights of Client Match. There's obviously a lot more. We could talk about it for a few hours, but I will hand you back to Kirti. Thank you.
Thanks, Peter. So let me transition the conversation into applications now. So, I mean, what we've shown so far is our new access points and software capabilities that allow you to take advantage of the performance of AC and the monitoring piece, which really, to me, is fundamental if you want to take the step towards all wireless office. Without that visibility, deep visibility, it's going to be hard to do this. Yet, as you look at the application space now, what's happening is our network architectures that we've built in the past, applications have been abstracted away from the network into VLANs. So every time there was an application that you needed to support on your network, you would map that to a VLAN. And this could be, it started off with VoIP, of course, where we plugged in VoIP phones into a voice VLAN or printers into a printer VLAN. But anything that happened after that, whether it was wireless VLANs or guest VLAN, contractors, quarantine VLANs, any new use case that emerged, you would quarantine it and put things on its own VLAN. And that worked fine for a long time on the wired world. But as you look at Link and what kind of application Link is, first off, it doesn't run on its own dedicated device. And most importantly, it has 5 different applications inside. You can do instant messaging, you can do file sharing, desktop sharing, voice, and video. Potentially all at the same time into 5 different flows. And to do Link properly, you need to really do away with the notion of VLAN-based priorities in the network, because it simply doesn't map. And you need to go up a layer and understand what the application is and what's happening inside the application to be able to prioritize. Because even within Link, there's some flows that are more important than others. Now the classic way to do it, and we've done it in the past, is to fingerprint Link RTP sessions. And we have done this in our infrastructure to be able to prioritize Link 2010. But as we started to talk to Microsoft a couple of years ago, the whole fingerprinting approach works fine, but it really doesn't give you visibility into the signaling side because it's all encrypted between the client and the server. So I'm guessing when I'm fingerprinting its heuristics and I'm guessing what's happening. But if there was an API that allowed me to hook into the server and know exactly what is going on from a call setup perspective, which flow belongs to which particular application within Link, that would give us a wealth of visibility into Link. And so we've innovated together, and Microsoft created a diagnostics API, which allows vendors to hook into it and get a view of that next level of detail, which flow belongs to which call setup process, etc. And using this API now, we have the opportunity to provide, of course, better QoS for all the different applications inside Link, do things like call admission controls based on the client match capability, and then post the call, analyze call quality, and map that to what the Wi-Fi network was looking like. So if you have performance issues with Link that your users complain about, you can go into the dashboard and correlate what was going on in the wireless network at the point in time that the Link call was misbehaving. But we're not stopping there. This is going to be introduced, and Pascal will talk a lot more about the API in detail. We're going to introduce this starting in Aruba OS 6.3. To give you an idea of the roadmap here, when we started out with Link, the first thing, of course, the entire industry, there was really no intelligence because it was all encrypted. And then the fingerprinting capability was introduced. Beyond that, what we have done is we are the only vendor to be certified by Microsoft at this point to run Link on top of their wireless networks. And today we are adding the visibility to Link calls using Diagnostics API. The next release will have capabilities to tie in client match with Link. And the effect of this is something like this. Let's say you have a set of Link calls, Link sessions on a given access point. In this particular case, I'm showing you there's a voice, video, desktop share, and a file share happening from 4 different devices on the same access point. At this point, if the voice and the video starts to misbehave, what will happen is the Link server in real time will update the controller and tell the controller these sessions are experiencing a lower MOS score or R value than before. I can look at what was going on that access point and shift the non-real-time sessions of Link over to other access points so that the real-time sessions, the MOS scores and the R values can be maintained. So this is to us, it's an instantiation of application-aware networking to the next level. Right? People call this software-defined networking, where applications interact with the network and optimize and change the behavior of the network itself. It's a version of that. We're going to innovate together in this area in a much more significant way. And in future releases, you'll see intelligent steering capabilities with client match tied to the application. And to us, using all these capabilities with Microsoft Link, we also introduced Air Group, which was the ability to now be able to have projectors be wireless, printers be wirelessly connected to the network. Together, what we are moving towards is moving away from a virtual LAN-centric architecture, which was built for the wired world. Instead of transitioning that into the wireless world, we are now saying that the world is really getting personal. It's around the user, their devices, and their applications. And the flows are optimized to work on top of the network on an individual by individual basis. And to us, this vision of a personal LAN is really what we are aiming towards, above and beyond just delivering the core infrastructure capabilities to enable this. At this point, I want to take a short tour into the demo land and look at what we're doing with Link.
Give me 1 second to log in. So here I'm looking at the Aruba controller, and I'm seeing a couple different users here. This is the standard client diagnostic screen. I believe it timed me out, so bear with me 1 second to log back in. Let's see. Kill a couple of these windows. Looks like I'm having a bit of a hard time getting to the controller.
We're going to come back to it later?
Yeah, let's come back to it in a couple minutes. Need to figure out why I can't get there. Maybe something with the wireless.
Why don't you transition back to the slide and see when it comes back.
Take a quick look.
All right. So while the demo is getting set up, let me just wrap the presentation here, and we'll transition over to Pascal after this. So to us, as we look at the evolution of the network, going back to starting with the wireless as an overlay to wired, making it an equal partner of wired, and now moving forward, replacing wireless with wired. There's really, to us, 2 paths that are becoming very clear in the industry. One path that is hardware-centric, still looks at tethering wireless back to the wired from an architectural perspective and from a philosophical perspective, which we think is really underachieving on the promise of what wireless and mobility can really be. And looking forward to where we need to go for a mobile-centric enterprise, wireless will become your infrastructure. The air and the spectrum will be the replacement for the cable, so you better get very, very comfortable monitoring and troubleshooting the air. The architecture of this network will be software-centric, not hardware-centric, to be able to enable applications, and that's the fundamental thing. Doing things like integration with Microsoft Link or other applications on the network that are mission-critical, making them interact with the network in real time, making that work together requires a software programmable control and data plane inside the network, and that's what we're going to innovate on. And finally, we're going to make this an open architecture. It won't be just Link. We're going to be integrating with many APIs, and we'll make the network itself available through APIs to our third-party partners, enabling a much more richer framework for basically layer 4 through 7 based networking over the air.